Even though the scene has perspective and depth, it's still not fully 3D until we have some shading. We can set up a light direction, and any vertices that point away from the light will be darker than the ones that point towards the light. So we need to find out which direction the vertices point in. We do this with surface normals. A surface normal is a vector that points orthogonally, that's at right angles, to the surface. When Blender exports an OBJ file, it includes vertex normals in the file, so all we have to do is read them in. Using the normal vectors, we can tell what slope the surface has and what direction it's pointing in. We can compare the direction of the normal with the direction of a light and shade appropriately. Let's update the app to read in normals from the OBJ file.
For this video, open the new starter project from the provided materials. This new project includes a camera where you can rotate around your scene. This will help you see your lighting better. Open up extensions.swift and update the metal vertex descriptor to include a float 3 allocation for the normals. We also have to update the stride, indicating that each vertex takes up 2 float 3s in the buffer. Normal is one of Model.io's predefined attributes, so update the Model.io vertex descriptor to include the normals. In shaders.metal, match the incoming vertex struct with the vertex descriptor. Build and run, and inspect the metal buffer to see the normals. We'll send the normal vertex to the fragment function and use a standard debugging technique to examine the normal value. In shaders.metal, create a new property in the vertex out struct for the normal. Next, we'll pass the normal from the vertex buffer in the struct in our vertex function. In the fragment function, return the normal value as a color. Build and run. We're using the normal as a color. A normal that faces directly up is 0, 1, 0. If you were to take this value as an RGB value instead of a vector direction, this value would be green. Similarly, the right-facing normals, where the value would be 1, 0, 0, 1 on the x-axis, will be red, and the back-facing normals will be blue. All negative directions have a color of less than 0, so they're black. These normals are the ones that came straight out of the file, so they're in model space. Let's rotate the train by 180 degrees and prove that. In renderer.swift, in init, let's update the rotation. Build and run, and the side of the train facing the camera is now blue. If we're going to test a normal's direction against a point in the world, we need to multiply the normals by the model matrix to put them into world space. So let's change that in our vertex function in shaders.metal. We're multiplying a float 3 by a float 4 by 4 matrix, so we add on a W value and then remove it again after multiplication. Column 4 of the matrix holds the translation values, and for determining the direction of the normal, we only need the model's rotation value, which is contained in the upper left 3 by 3 matrix. The model's scale is also held in the upper left 3 by 3 matrix, but as long as we're scaling the same on all axes, this will be fine. Build and run, and check out the normals pointing in the X direction. These are now darker than they should be. In the GPU debugger, we can check out the fragment color. First, select the draw command for the train's cabin, then click the bug icon, choose a fragment, and then click on debug. Now we can view the actual values for the highlighted fragment. We can see that the red value is 0.5 instead of 1, and that is because we scaled the train by 0.5. When using normal vectors and comparing to other direction vectors, they should always have a unit length of 1 so that we're comparing like with like. Back in the fragment function, we can use the normalize function to give the normal vector a length of 1. Build and run, and the normal facing in the X direction is now bright red as it should be. To avoid confusion about what space the normal is in, let's change its name to world normal. It's possible to do lighting in camera space too, but we're going to be doing it in world space. We're also going to need the fragment position in world space too, so let's add a new property to the vertex out struct and update them in the vertex function so that we'll be able to use it in the fragment function shortly. Build and run to make sure it still works. Now that we know which direction a vertex is facing, if we had a light in the scene, we can calculate how much the vertex should be lit and we can shade the models.